Hi, everyone. It's pretty exciting to be here today. Thanks for coming. It's an honor to start this event. I'm very excited about all the talks they're going to have here, to listen all the cool things you do with Rust. I would like to talk today a little bit about how Rust enables us to write safe software in a very unsafe world. Just a quick introduction about myself. I am a principal engineer at Amazon AWS. I have recently joined the AWS Rust platform group, which is led by Nico Matsakis, where we really focus on helping Rust builders, both internally and externally. I'm also the co-leader of the Rust compiler project named Stable Mir, where we are working to introduce APIs to the compiler. So tool developers can use the compiler as a library to build sophisticated code analysis tools. I've also been working on the experimental feature for function contracts and type invariants in the Rust compiler and the language itself. Before I joined the AWS Rust platform group, I was working as a leader of the development of Kani, which is a Rust verification tool. It does form verification. I'm going to talk briefly about it at the end. And before Rust, I was actually a C++ developer. I've done lots of Java, Python, but before Rust, the language I'll be like championing was C++. And coming from that C++ world, my perspective was I liked to be able to build efficient software, right? That was the reason why I liked C++. I liked to be able to have control over my software. And I just accepted the fact that I had to deal with memory management, that I had to deal with seg faults and everything else. And then I started using Rust. And it was very interesting. As soon as I started using Rust, I just realized that efficiency does not have to come at the cost of safety. And it's actually the other way around. It's pretty cool how Rust, basically with the same strong types system, it uses this, the compiler is aware of this. And this is what makes Rust efficient and safe at the same time. This type system will enable the compiler to create optimizations based on the type system, and it will also enable the compiler to create all these safeguards that we all know, including the borrow checker. So this is a pretty cool realization. That's like, wait a second, I don't have to deal with memory violations, and I can still be fast. That was amazing for me. But Rust, with Rust, we still are very much aware there are things the compiler cannot check for us. There are some use cases out there, for example, boundaries with a different language where the compiler doesn't have enough information to ensure safety. And for those specific cases, Rust still enables us. It still has features for us to do this safely. So it will still provide that low-level control, but really only when you need it. And basically the way the Rust does this is there's a language inside the language. So, and by the way, both of them have their own mascot. You probably all know Ferris, but there's also Koro, which is the mascot for Unsafe Rust. And so basically, Rust has all these constructs that are safe, that the compiler can guarantee safety. And then there's the extension, which is Unsafe Rust, that besides all these features that Rust provides you, it also adds some features that the compiler can no longer reason. It can no longer guarantee safety for you. Hence, it's called unsafe. It doesn't mean that if you use, it will be unsafe, but the compiler just cannot give you the guarantee. And the way you can use unsafe Rust in Rust is basically by using the unsafe keyword. This is a way for you to tell the compiler, now I want to use the unsafe Rust. And this is a pretty cool feature because it actually avoids you to having to mentally think about safety all the time. It allows you to basically abstract this. You know you're safe as long as you're outside of this unsafe world. So you can do your coding, you just really worry about the correctness, the function correctness of your code. But in the case where you need it, now you can explicitly say, I want to use these features. You are telling the compiler, I want to do this, and I will do it, and this is my intent. You won't do it by mistake. This unsafe keyword also allows you to audit. Let's say you're looking at you're reviewing a code review, or you are looking at a new dependency. Having that unsafe there is a great way for you to know where you have to be careful. Maybe it's an API that if you can avoid, you can avoid. That will help you stay safe. And this also limits the amount of unsafe features that people use there, because no one really wants a code that has everything is unsafe. Then it's basically going back to C, C++ world. So now, when we look at this, there's a question of how do we stay safe? There is unsafe there. We can't ignore the fact that there is unsafe. So first of all, just don't use unsafe. And I would say 99% of the case when you're writing Rust, you're perfectly fine in the world with safe Rust. And this is the cool thing. It's really only needed sporadically. And a lot of times, performance, you won't gain any performance from using unsafe, because the Rust compiler and the Rust in the library is very much optimized for a safe code. But it's also good to be aware that even though you are using safe APIs, underneath the safe API, there could be unsafe code. So make sure you do your homework when you're adding a new dependency or, again, code review. Keep an eye for those unsafe words. And this is the other thing is just enforce best practice. I think this is a general advice, unsafe or not unsafe. But Clippy and Rust compiler, it provides specific links for unsafe code to help you stay safe in unsafe. But what I really want to talk about are these three things when it comes to using unsafe code. I would like to talk a little bit about how do we design for safety? How can we make sure our design is accounting for unsafe code? And this is also a great thing for us when I said we mentioned about auditing, is also a great way for you to audit, is to know the design. Is this a good design? Are they using unsafe properly? The other thing I want to talk about is testing. How do we test unsafe code? And finally, I also want to talk about how do we prove safety of unsafe code? So design for safety. Basically, design for safety follows very similar methodology than just designing in general. When we're creating an API, we always think about what's the contract of that API? What are the expected inputs? And what are my expected outputs given that input? So unsafe Rust, in that sense, is very similar. But with unsafe Rust, we really want to be careful to really document really well and test these contracts really well so we know we are safe. And again, this is a feature. The way Rust allows you to establish this contract is through the unsafe keyword. And the unsafe keyword, it has dual meaning to it. It has two sides. It's the same way when you have an unsafe function, which is where you declare your contract. You are telling basically when you put a function and you said this function is unsafe, you're explicitly saying there's some conditions, there's some inputs to this function that I cannot guarantee safety of my code. So now you have to list those conditions. So the callee of your function know what the conditions are, and they have to ensure that those conditions are met. And the way they do this is also through the unsafe safe keyword, which is now you're going to write unsafe, and you're going to be like, this is why this is safe, because I've checked these conditions, for example. So when we're designing for safety, what we want to do, as I mentioned, is we really want to limit the usage of unsafe Rust, because we don't want to have to worry about safety in your entire crate. So that's why we create these safety abstractions. And safety abstractions are basically safe functions and that you are able to use unsafe inside safely. And usually you encapsulate that, so you encapsulate those safe code with those safe interfaces. And that could also include a type. And you guarantee the safety of your abstraction by either performing runtime checks or by encoding the data structure type invariants. For example, vector, we keep capacity, so we know the memory that we allocated. What's the memory allocated? Do we need to allocate more? So capacity, for example, and length is it helps you with that type invariance, is what helps you stay safe. And a very important thing when you're designing for safety and when you're thinking about safe abstractions, safety conditions should never leak to the safe world. So a safety condition should never be exposed to the callers of your safe APIs, which means for whatever possible safe value of your inputs, whatever safe state you stay in, there should be no UB whatsoever. So this is very important. So this is what really allows us to have this modular thinking. This is what really allows us to be safe everywhere else. Because if you leak a condition, now user has to worry about that condition to stay safe. So this is why it's very important. This is what really makes an abstraction safe. So here's an example of a safety contract. So I'm going to look quickly at this is basically the implementation of ask-to-character in the Rust standard library. You can see here that they use an enum with 128 variants, and they use a representation of U8, so it's a 1 byte size. So this use Rust type system to guarantee these type invariants, that you have a size of U8, 28 variants, and it sets specific values for the discriminants, so which means from 0 to 127, those are valid byte representation of this structure. Everything else would be UB if you set this. And here you can see that this is an unsafe function for this structure, where it allows you to create the structure from a byte without any validation. So here the contract, the way it's established is through a safety comment where I'm like, hey, this byte here, it has to be between 0 and 127. You as a callee have to guarantee this. And it's also interesting that even though we're in an unsafe function, we still explicitly use unsafe when I'm using the unsafe operation and stating why that is safe. It is safe because my callee has guaranteed that's safe. And here's a safe abstraction of the same function we just showed, which is I can create the same structure with a byte, but I do that runtime check for you. And if that runtime check does not pass, it returns none, otherwise returns the sum object. Again, now you can say the safety is because I have checked the Bayesian range. So now this is a safe abstraction. Your callee can call this with any byte, and we know there won't be undefined behavior. The other thing I want to talk about is unsafe traits. Unsafe traits is a very interesting feature in my mind, which it allows you to write generic safe abstractions. So basically, unsafe trait will define a safety obligation of a type, no longer of a value. So you're saying this type respects these conditions. So the other cool thing about this unsafe trait is that the implementation is what ensures the type will satisfy those conditions. And you as a callee of a function, a user of a type, you don't have to care whether the type, you don't have to know how the type satisfies those conditions. This is the implementer role. So an implementer of this trait, of an unsafe trait, is who guarantees that the trait is safe for those conditions. And so this is cool because it doesn't break encapsulation. So if you, let's say, if your type internally has some safety conditions, you just don't implement a certain trait. So it's you as a type. It's, again, it's a contract of your type. It's a property of a type, instead of now the user having to verify that. Here's an example. I created this dummy function that basically spit out the bytes of your object. So basically, I convert an object, a reference of an object, to a reference of bytes. So let's say, so basically, it's a serialization API that allows me to dump the bytes. However, how do I know I'm safe? So if you look at the safety conditions of this sref unchecked, it will say that the caller must ensure that the pointer is dereferenceable. What does that mean? It means that it has to be aligned, proper size, allocation, aliasing, but also that the value of this reference, the reference point to, is a valid value. But I don't know this. I'm just writing this a generic. I don't know T. And this is where unsafe traits come in. I can actually make a safe abstraction by adding a trait bound. I can say, you know what? I create this unsafe trait, and I explicitly say, you have to implement this if and only if all the bytes are always initialized. So for your type, you can't have any uninitialized byte. If you don't, you implement the trait, and now callees can use my function safely without leaking anything. Just a quick note, there are a lot of traits that does this even safer. So zero cop is one of them. There's a safe transmute project as well that they're looking into this condition. So now let's talk a little bit about testing the unsafe code. When we're talking about safety in Rust, we're really talking about absence of UB, of memory safety violations, and these are actually pretty hard things to check. If you have a memory violation, it can happen that your program is going to crash. It can happen that it's going to misbehave. You might leak some security information. And it's hard to test because from a user perspective, you actually don't know what's going to happen. Depending on the compilation flags, it might, it's one of those cases where you add a print, now that issue is gone. So it's a very flaky issue. And just to quick look at an example of like the same case I was looking at before, I created now a pair, a representation C, because I know I want to keep the order right of my types. And I say I have a pair of type T and U. And I go and implement my initialized bytes. And I say, well, if T and U also implements initialized bytes, I'm good, right? Exactly. No. Why? Because of padding bytes. Padding bytes are actually not guaranteed to be initialized. So I go and create my unit test for this. I have a pair of I8 and I64. I don't know, it's a random one. And I put 13 and 12 there. And now I go and say, let me make sure my byte representation is correct. Do I have a 0 byte? Do I have a 13 byte? Do I have a 12 byte? Yes, good. I'm good to go. This is not necessarily the case. And let's look at what happens when we run this. Oh, there you go. That's good. But what happens if I remove this comment here? Let me print what we actually serializing. So now you can see it, sure, 13, 0 is there, 12 is there, but we have all these other bytes, and what is in there? And interesting enough, let's see if that will work. If I run this, again, the bytes change, because now the information will depend on the memory, or what was in the memory before. And this could be a security issue, could be leaking some information. So how do we test this? How do we guarantee, how do we know this is not right? And this is where I want to talk about Miri, which is a tool that you can execute, even Playground, that will help you. There you go. If you run this with Miri, now you're going to see there's an error, an undefined behavior. You are using uninitialized data. So Miri will help you with this. And Miri is a tool that right now it comes on only in the nightly toolchain. You can use on either in Rustop or you can use in Playground to help you find those issues. And basically, I want to talk a bit about Miri. So Miri is a great tool for you to check for undefined behavior. It is And it basically is an interpreter of the internal representation of the Rust compiler. It is also a great alternative to mem sanitizers and Valgrind and all other tools that is also very helpful when you're doing unsafe things, to make sure you're not doing and you're not violating any memory access, but also it catches Rust-specific UBs. Value validity, it's something that you're not going to be able to detect using Valgrind, for example. So it's a very important tool that if you are using Unsafe, you should consider using Miri with all your tests, integration tests, whatever you have. The main limitation is that it does not work across FFI. The same way the compiler needs that information about your Rust code, so does Miri. And some people say it can be slow. I haven't run like massive tests, but it's probably not going to work if you run a massive test in it, like an end-to-end test. And finally, the last thing I want to talk about when it comes to staying safe is proof safety. So as I said, a safe code, the Rust compiler give you the guarantee you're safe. But you can still prove safety with Unsafe. And the way you do this is by applying formal verification. And I don't know if anyone here has tried formal verification before, but basically, formal verification tool, the way it works is it will compile your Rust code plus some specification, some annotation that you might have to manually add, and it will compile down into a logical formulas. And those logical formulas now are going to be given to a solver, most of the time set solvers, theorem solvers, that will now verify whether your Rust code respects your specification. And this is actually verifying all the possible combinations of paths you have in your code. And this tool, any verification tool, it usually is going to return either you succeeded, whether it's proven that you are following your spec. It might not succeed, so it is an undecidable problem. So sometimes it might not succeed. And sometimes it will fail. And usually when it fails, it will return you a counterexample, which usually is an input, a concrete input, where your code actually fails that specification. And Rust actually has a very interesting ecosystem of verification tools. There are many verification tools out there, and this is just the beginning of a list. The list is bigger, and it keeps changing. There's a lot of research happening in this area. So, and each one of them has its strengths and also some weakness. So if you are considering looking for verification, you have to do a bit of your homework to see which one suits me best. And also, maybe you might want to use more than one. So how do I prove my code is safe? So if you follow my first advice of creating safety abstractions, you can actually apply modular verification to prove your code is safe. You basically have to verify the safety contracts of your unsafe functions. Are they enough? Given my preconditions, am I free of UB? And the other thing is, do I maintain my type invariant if I'm using a type to encapsulate my unsafe code? You can verify that all the calls you make for unsafe code, unsafe functions, also respect their conditions. And finally, you have to verify the type invariant for all your public functions. So you need to make sure that at construction time, all the objects you can build safely respect the type invariant, and also any change to that object, any safe or mutable access to your type, also will never leave your type in an unsafe. It will never break a type invariant. And this is quickly how this would look like, for example, in Kani, which is the tool I just mentioned that I used to work on. Here, basically, I'm looking at, as this example, I'm going to look at a C string, which is, again, from the standard library. It's a borrowed C string, which is a slice of bytes that always must be null terminated. So here's where we write the invariant. So the same invariant I just mentioned, it has to be null terminated, so it has to have at least one byte. the last byte has to be null, and nothing in the middle can be null. And now, let's say there's an unsafe function. Here, I encode the safety conditions as a functional contracts. So we have a requires clause where I describe all that safety condition about the bytes that are being given to me that basically has to respect the same conditions of my type. And I ensure that at the end, the result is safe. So I want to make sure my variant has not been broken. And for Kani, the way you test this, the way you verify this is through a harness. You write a harness very similar to your unit test, where you create a non-deterministic input, which means it's an input that the values are not constrained. You use Kani for this. Just a quick call out, this harness right now, it's a simplified harness, so it's bounded. So right now, this only checks your code for anything up to 32 bytes. And now you run this, and now Kani will tell you, you succeeded. So given those conditions, Kani has instrumentation internally to make sure there's no UB, at least for some of the UBs, not all of them. And it will return that it's successful. I'm not going to run this today because it takes about 40 seconds, and you don't need to wait for it to see. But you just have to trust me on this one. And finally, one last thing I would like to bring is Rust is constantly evolving, and the same is true for Unsafe Rust. There are a few projects out there, there's a few changes that I think is worth keeping an eye for, and even if you want to contribute or try it out, I highly recommend you to go and help. One of them is unsafe fields. There is RFC that has been created, and a experimental feature in Rust that allows you to declare the fields, some of your fields, as unsafe. Why would you do this? For safety hygiene. So now it's very explicit when you're making changes to a field that could potentially break a type invariant. For example, VEC capacity. If I set a wrong VEC capacity, this breaks my type invariant, and I can, in the future, have a safety violation. And it's still being discussed what exactly is going to be unsafe with unsafe fields, but for example, writing to unsafe fields might require unsafe blocks. The other one that I want to talk about is functional contracts and type invariant. The same way I just showed the Kani example with the type invariant and safety attributes. This is something that almost all verification tools out there will have, and they have their own safety language, their own attributes. This is something we've been considering bringing into the Rust language. So there's again, an experimental feature that allows you to set this up. And then the idea would be, this would unify the contract language. So whatever language you add today to your crate, someone else in crate B can use the same contracts to verify the code. They might not use your same tool. It's OK. It also will allow you to opt in for runtime checks. So some of these contracts might be verifiable at runtime, might be checkable. So this will also be added with an option, similar to like debug asserts. And finally, the last one I want to talk about is the Rust standard library verification. There's an effort which is set up as a contest to help you verify the safety of the Rust standard library. So basically, this project has a North Star of being able to verify the safety of future releases of the standard library. This is to a very much starting project, but that's kind of our North Star there. And it also to help us assess the readiness of verification tools, help us identify bottlenecks that can guide further research. So this is the link for it. And just to recap, I just want to say first is Rust is a safe and efficient language. This is very important. This is what makes Rust, in my opinion, so awesome. It will provide you low-level control through its extension, which is Unsafe Rust. And the safety of Unsafe Rust rely on the safety contracts. And you are responsible to verify that contract, either manually or also with tools. And I want to make sure we talk, that's what I want to make sure. So we talked about some of these tools. There are awesome tools out there that's worth checking out as well. As I said, there's many of them. So And just remember, great power comes great responsibility, so stay safe if you do use Unsafe. Thank you.